Every vehicle we build runs on rubber tires. So why does the most powerful land vehicle on Earth still roll on bare metal? Trains aren't just a relic of the past. They're the backbone of America's supply chain. At any given moment, thousands of locomotives are hauling grain, coal, cars, and chemicals across the continent. The numbers behind this are staggering. Railroads move about 40% of all long-distance freight ton-miles in the United States. That means nearly half of every ton of cargo that travels more than a few hundred miles gets there by train, not truck or barge. If the rail network vanished overnight, it would take an extra 80 million trucks to keep goods moving, and fuel use would skyrocket. Passenger service, while smaller in raw tonnage, is no less impressive. In a typical year, American rail carries billions of passengers. Amtrak alone logs nearly 5 billion passenger miles annually. Urban transit systems add tens of billions more, connecting cities and suburbs in a daily rhythm that few people even notice. This scale is almost invisible, but it's everywhere. From the flour in the bakery to the steel in a skyscraper, rail is woven into the fabric of daily life. What is most surprising isn't just the volume, but the efficiency. The shocking stat: a single gallon of diesel can move a ton of freight nearly 500 miles on steel rails. That is not a marketing slogan. It is a figure confirmed by the Department of Energy and the Association of American Railroads. On the highway, a heavy truck can't come close. The reason for this gap is not obvious from the outside. It is not the size of the engine or the length of the train. It comes down to a disorienting question: why does bare steel, not rubber, unlock such massive efficiency? When so much of the nation's economy rides on this one engineering choice, every detail matters. The answer to why locomotives do not have tires isn't just about tradition, it's about physics and economics, and the relentless pursuit of a solution that is already close to perfect. Steel wheels rolling on steel rails unlock a physics advantage that borders on the unbelievable. The secret lies in rolling resistance, the tiny force that tries to slow a wheel as it turns. For a steel wheel on a polished rail, the rolling resistance coefficient sits at about 0.001. That means for every 1,000 pounds a train carries, only a single pound is lost to friction. Compare that to rubber tires on asphalt, where the coefficient jumps to between 0.01 and 0.03. That is 10 to 30 times greater resistance, and it is why trucks burn through fuel so much faster than trains. The difference is not just academic. It translates directly into energy and dollars. The classic claim, 1 gallon of diesel moves a ton of freight nearly 500 miles, comes straight from this gap. On highways, a fully loaded truck might get 6 miles per gallon. On rails, the same gallon stretches impossibly far because the steel-on-steel interface wastes so little energy. Engineering handbooks back this up. The force needed to keep a train moving at speed is just a fraction of what is needed for a rubber-tired vehicle of the same weight. Why does steel glide so easily? The answer is counterintuitive. The contact patch between wheel and rail is tiny, just a few square millimeters, so the steel does not deform much, and almost all the engine's power goes into forward motion, not fighting the road. Rubber, on the other hand, squishes and flexes with every turn, bleeding energy as heat. For a locomotive, that means less work against friction and more work moving freight. This advantage is so pronounced that if you swapped steel wheels for tires, the result would not just be lower efficiency, it would be disaster. The tires would overheat, shred, or even burst under the immense weight. Steel on steel is not just tradition. It is the physics engine that makes railroads the champions of long-distance transport. But this near-frictionless ride comes with a twist. The same smoothness that delivers efficiency also creates a counterintuitive problem: almost no grip. And that is where the real engineering puzzle begins. steel-on-steel contact creates a strange paradox. The very feature that makes trains so efficient, the near-frictionless glide of metal wheels on metal rails, also means there is barely any grip. In physics terms, this is called adhesion, and for locomotives, it is a constant source of tension and risk. Dr. Emily Rivera, a specialist in wheel-rail standards, sums it up. The adhesion envelope of steel on steel, when managed by modern systems, gives us a safety factor that rubber simply cannot match for 20,000-ton trains. But that safety margin is razor thin. Under dry, clean conditions, the coefficient of adhesion, represented by the Greek letter mu, hovers around 0.3. That means only 30% of a locomotive's massive weight can be turned into usable pulling or braking force before the wheels begin to slip. If the rail is wet, mu drops below 0.15, about 15%. With oil or crushed leaves, it can fall to the danger zone of 0.08, 8%, or lower. For a 500-ton locomotive, the difference between moving a train and spinning helplessly on the rails can be as little as a light drizzle or a patch of autumn leaves. This is not a theoretical worry. The Federal Railroad Administration's data shows that the adhesion limit is the hard wall every engineer must respect. Push just a bit too far, and the wheels lose their grip entirely. Acceleration becomes a crawl. Braking distances stretch from a few hundred feet to nearly half a mile. On a bad day, stopping a train on wet rails can take 1,000 feet or more, several city blocks, before friction finally wins out over momentum. The low grip paradox flips the script on everything we expect from heavy vehicles. Trucks rely on thick rubber tires to claw into the pavement, but trains must make do with a contact patch the size of a coin. The reward is unmatched efficiency, but the price is a constant battle against slipping, sliding, and the ever-present risk of runaway momentum. This disorienting problem forced engineers to invent solutions found nowhere else in transportation. The story of how they did it begins with the geometry of the wheel itself. The secret to how a train steers itself is not found in electronics or hydraulics. It is carved right into the steel wheel. Every locomotive and rail car rides on wheels that are not perfectly round. Instead, the tread is machined with a subtle cone shape, about a 1% taper, or 1 millimeter of radius change for every 100 millimeters of width. This tiny angle is the heart of a self-steering system so elegant it barely looks like engineering at all. Here is how it works. When a train enters a curve, the wheel set naturally shifts sideways on the rails. Because the wheels are conical, the one on the outside of the curve rides on a slightly larger diameter, while the inside wheel runs on a smaller one. That means the outside wheel covers more distance with each turn, gently steering the axle back toward the center of the track. There is no need for steering wheels, pivots, or computers. The geometry does the work, keeping the train centered and stable, even at high speeds. But the conical tread alone is not enough to guarantee safety. Each wheel also has a flange, a raised lip usually 30 to 45 millimeters tall, set at a steep angle. The flange acts as a last resort. It only touches the rail if the wheel set drifts too far or if the track geometry is off. Under normal conditions, the flange barely comes into play, minimizing wear and noise. But if things go wrong, a sharp curve, a track defect, or a worn wheel, the flange is the final guardrail against derailment. These details are not just tradition. They are codified in standards like AREMA and UIC, which specify the exact conicity, flange height, and profile tolerances. Even a fraction of a millimeter out of spec can mean the difference between flawless self-steering and a dangerous wobble. For trains, the wheel is not just a circle. It is a quiet masterpiece of passive engineering, guiding thousands of tons of freight and millions of passengers with every turn. The 500 mile per gallon figure sounds almost impossible. like a trick of math or a marketing exaggeration. But it is real, and it is the direct result of steel wheels gliding over steel rails. This is not just a physics curiosity, it is the backbone of rail's economic power. According to the Department of Energy and the Association of American Railroads, a single gallon of diesel moves 1 ton of freight nearly 500 miles on the rails. That is not just a little better than trucks. It is 10 times farther per gallon than a fully loaded tractor trailer on the highway. This efficiency is not a minor perk. It is the reason railroads thrive in an era of high fuel prices and climate pressure. Every year, United States freight trains save billions of gallons of diesel that would otherwise be burned by trucks. That translates into lower shipping costs, fewer emissions, and a supply chain that can stretch from coast to coast without breaking the bank. The numbers are so dramatic that if rail lost its edge, the cost ripple would reach every supermarket shelf and factory floor in the country. But the payoff comes with a twist. The same smooth, nearly frictionless ride that lets a train sip fuel so sparingly also means there is very little grip between wheel and rail. The reward for this near-perfect efficiency is a constant battle against slipping and sliding, a challenge that trucks with their grippy rubber tires almost never face. The story of why locomotives do not have tires is really a story of how engineers chase the ultimate efficiency and then have to invent new solutions for the problems that come with it. Imagine rolling a 500-ton locomotive onto rubber tires and asking it to do the work of steel wheels. The physics does not just bend, it snaps. Under the weight of a modern freight train, a single axle can press down with 30 tons of force. Even the toughest truck tires, rated for heavy highway loads, are not built for this kind of punishment. The result is not a slow fade. It is a catastrophic failure. As the locomotive starts to move, the rubber flexes and deforms, generating far more heat than it can shed. Within minutes, the tire temperature soars past 150 degrees Celsius, the softening point for most commercial rubber compounds. At this threshold, the tread begins to break down, belts separate, and the sidewalls start to bubble. Tests on heavy off-road tires, the closest analogs to what a locomotive might use, show that under a 30-ton load at moderate speeds, the rubber heats up so quickly that it can shred itself apart in less than half an hour. Burst pressures climb above 250 pounds per square inch, far beyond what the tire can contain. The failure is not subtle. The tire explodes or peels away from the rim, leaving the axle grinding against the rail. In historic experiments, like the Michelin rail bus trials of the 1930s, rubber tires melted and delaminated after just a few miles of continuous running. The problem is simple, but effectively unsolvable. Rubber's rolling resistance is 10 times higher than steel, so all that wasted energy turns straight into destructive heat. No amount of engineering tweaks can overcome this basic fact. The physics of heat buildup, deformation, and catastrophic blowouts simply make rubber tires a non-starter for locomotive duty. The only reason steel wheels work at all is because they barely deform, keeping rolling resistance and heat astonishingly low. That is the final answer to the question. Why do locomotives not have tires? Because the tire would never survive the job. In the early morning hours of September 15, 2014, a CSX freight train thundered through a curve near Cecil, Alabama. The train, weighing over 6,000 tons and stretching nearly a mile, was running just a few miles per hour over the posted limit. On car number 42, a single wheel's flange had worn down to 3 millimeters, just 1 millimeter past the industry's red line. To the naked eye, that difference is barely the width of a dime. But in the world of steel wheels and rails, it's a chasm. As the train leaned into the curve, the worn flange lost its ability to keep the wheel set properly guided. Instead of hugging the rail, the wheel began to ride up and over it. In a matter of seconds, the car derailed. The National Transportation Safety Board's forensic report found that this tiny excess in flange wear, just 1 millimeter, was the crucial factor. The self-centering geometry of the conical wheel in its flange, so reliable under normal conditions, failed when the margin slipped below the prescribed limit. No catastrophic brake failure, no sabotage, just the physics of steel on steel revealing its razor-thin requirements. When tolerances drift, the system's efficiency turns on itself. The difference between a seamless journey and disaster is measured not in feet or inches, but in fractions of a millimeter. In this world, perfection isn't a luxury. It's the line between control and chaos. Precision is not a buzzword in railroading. It is a daily ritual, measured in fractions of a millimeter. On the main lines, maintenance crews work with a level of scrutiny that borders on obsession. Rail grinding machines sweep along the tracks, restoring the railhead to within plus or minus 0.3 millimeters of the ideal profile. If a segment drifts outside that envelope, it isn't a minor blemish. It is a $1 million risk. Every pass of the grinder is logged, every deviation flagged in the track maintenance system. In the wheel shops, laser profilers scan each wheel set for tread wear. The standard is unyielding. No more than 1.5 millimeters of wear on the tread, and flanges must stay within a hair's breadth of the ARIMA limit. When a wheel crosses that line, it is lifted from service and placed on a lathe. The machinist's task is surgical, shaving away just enough steel to restore the perfect conical shape, not a fraction more. John Joker McAllister, a senior foreman with Union Pacific, puts it plainly. We drive a 12-inch laser across the rail 3 times a day on our main line. If the profile deviates by even 1/10 of a millimeter, we schedule a grinding crew. The cost of a derailment is millions. A half hour of grinding is a tiny price to pay. This culture of relentless measurement and correction is the invisible shield that protects the efficiency and the safety of the entire system. In railroading, perfection isn't an aspiration. It is the baseline for keeping 40% of America's freight and billions of passengers on track. Speed has always been the ultimate test for steel wheels. As trains pushed past 200 miles per hour, the physics that once delivered perfect stability began to turn against them. Professor Hiroshi Tanaka, a high-speed rail engineer in Tokyo, describes the challenge. He says that reducing wheel conicity and tightening rail tolerances were the 2 most effective levers to suppress hunting above 300 kilometers per hour. In Japan's Shinkansen, engineers cut the conicity of the wheel tread down to just 0.3% and paired it with active suspension. This combination tamed the dangerous side-to-side sway known as hunting oscillation, allowing trains to run safely at nearly 200 miles per hour. But the solution came with its own demands. Rail profiles had to be kept within 0.2 of a millimeter, and every wheel set monitored for the slightest deviation. Meanwhile, in the heart of Paris, another twist on the wheel story plays out underground. Sébastien Dupont, chief engineer for the Paris Metro, explains how rubber-tired trains thrive in a different niche. He says that rubber tires give us the agility we need in dense city tunnels, but the heat management limits us to passenger loads. On lines like Metro 14, rubber-tired cars can climb grades as steep as 13%, impossible for steel wheels, while delivering quick acceleration and a whisper-quiet ride. But these benefits come at a price. Tires wear rapidly, cannot handle heavy freight, and would overheat catastrophically if pushed to mainline locomotive loads. The arc of wheel and rail innovation stretches back nearly 2 centuries. In 1829, Stephenson's rocket ran with fixed flanged wheels, a leap that made reliable high-speed rail possible for the first time. Every advance since, from conical treads to active suspension, has been a refinement, not a reinvention. The story of the locomotive wheel is not about holding on to the past. It is about engineers, across generations and continents, relentlessly perfecting a design that still outpaces every alternative. Today, steel wheels carry 40% of America's freight and billions of passengers, fueled by physics so efficient that a single gallon of fuel moves a ton nearly 500 miles. Rubber tires would shred, melt, or deform under this load. That disorienting truth has held for 2 centuries. Sometimes the most radical engineering solution is refusing to reinvent what already borders on perfect. The next time you hear a train, remember, the real twist is how little has changed.